So we'll talk about the simultaneity and time dilation, 时间同价, and the relativity of length, 忘记中文是什么, and the Lorentz transformation, relativity of velocity, Doppler's effect for light, and the momentum and energy. So this will be about the famous identity called the EMC square. Maybe you have already know it in the primary school, but actually you may not know what it is. So first of all, Einstein's special relativity, special theory of relativity is based on two postulates, or you can regard it as two assumptions. So the first one is relativity postulate. The law of physics are the same for observer in all inertial reference frame. No one frame is preferred over another, because we actually don't know whether we are stationary, because actually we are on the Earth, and actually we know the Earth is rotating, and actually is rotating around the Sun. But how about the solar system? Is the solar system moving? Actually, it is, I think. Is there anything that aren't really moved? We don't know. But at that time, the scientists believe in the ether, 以太. Because in the past we know that for sound wave, the sound wave need to propagate in the air. Without air, the sound cannot propagate, or the sound can propagate in some solid object. So that in the past, maybe they are in a war, then they just crawl on the floor, and then they can hear, or there are some horse coming, or something moving, then they will know, or the enemy are approaching, or something like that. So the scientists will think whether the light needs some material for propagating, because even in free space, the light can propagate, because between the sun and the earth, it is free space, there are no air. But whether there are some material that can propagate the light, at that time, more than 120 years, the scientists tend to believe there is something called ether to propagate the light. However, they fail, but actually I will discuss this later in page 5. So let's come back. So another postulate for the relativity is the speed of light postulate. We try to assume that the speed of light in vacuum has the same value c in all directions and in all inertial reference frames. This is hard to imagine because, just an example, for example, A and B are separate in, for example, A and B are separate in for maybe 10 meter. For 10 meter, there are 10 meter between them. So if A is moving 1 meter per second towards B, then it takes 10 seconds for A move to B. And if B is moving 2 meter per second and A don't move, then B need to spend 5 seconds to move to A, right? And if both of them are moving, they only need 10 divided by 1 plus 2, which means 3.33 seconds, so that they can meet each other. And if A is moving, then he will see that B is moving at 1 plus 2 meter per second, right? This should be what you have learned in primary school. And for B, similarly, you find A is moving 3 meter per second toward him. However, it tells you that suppose there's a photon moving at the speed c, and you try to move at the velocity v. V can be very large, can be 0.1 c, but in this reference frame, you still find the light have a speed c. If you move away, you will still find the speed of the light is still c. This doesn't really match our intuitive sense. However, the experiment more than 100 years ago find that this is really correct. So Einstein make this postulate. So light happens to travel at this ultimate speed, no matter how you move. Oh, okay. I need to emphasize the term inertia. Inertia means constant speed without any acceleration. Then we call it inertial. 惯性的坐标系，惯性坐标系. So we call it inertial reference frame. It can move with a constant speed. It can be stationary, but it doesn't have any acceleration. Then you will always find the light travel in the speed of c. At that time, people try to accelerate some particle. And they find that no matter how much energy you give to the particle, it cannot be faster than the speed of light. So it will try to converge to the speed of light. This is an experimental result. They try to accelerate it, but they can. So this is the speed and the kinetic energy of the particle. And then they find that the speed cannot exceed the speed of light. And in the last section of this chapter, you know, it's something like if a particle moves faster, the mass will increase by a factor. So if you move faster, it will be heavier. Then you need even more energy, but you can never reach speed of light. And the experiment, this is one of the experimental results, tells you that c is an ultimate speed. And this is another experiment. Originally, as I mentioned, people believe that there is something called ether to propagate the light. So the scientists try to design some experiment to prove the existence of the ether. However, all of them fail. Maybe on this page, but here this is about the Michelson interferometer. So I just skip the chapter 34, 35, and 36 because there are something like the interference and diffraction, 干涉、扰射那些. So if I don't really talk about the Fourier optics, then it will be something like you learned it in high school. So I think it will be more interesting to directly go to the relativity and the quantum mechanics. So the Michelson interferometer can measure the distance between them because, for example, if you want to measure the length of a book or length of a desk, you use a ruler. But if you want to measure something very short or with very high resolution, you really need to use a ruler with a smaller resolution. But usually for ruler is something like 1 millimeter or something like that. For some other ruler may be more accurate, but not accurate enough. So we'll try to use something with a very short wavelength. As you know, light has a very high frequency, so the wavelength should be very short, as I mentioned in chapter 3. So we'll use the light to really measure the distance between D1 and D2. And if there are some tiny difference, it will form a different interference pattern according to the difference between these two paths. So it try to observe here there is a source propagating a light, and then this is a splitter. So half of the light go to this path and half of the light go through and go to this mirror, and the light go back, and then some of the light will go to this T, which is an observer. Then here we can observe the interference pattern of the light, and the pattern will depends on these two distance. So there's a equation like this, but it doesn't really matter. So Michelson and Morley try to design an experiment which is the most famous failed experiment. They try to prove the existence of ether, but failed. However, they become famous. The conclusion of this experiment is that the speed of light is a constant for different inertial reference frame, because if it is very large, then and the Earth is actually rotating, so that you can assume that there are some other movement in these two directions. If the ether is really exists for propagating the light, it should be moved or have some relative movement between these two paths, which will influence the distance for these two paths, or the time for the light to travel between these two paths, and then it will influence the interference pattern. But it found that actually the ether does not exist, and the speed of light is always speed of light. No matter in this direction or that direction, it's still speed of light. So that's why Einstein made this postulate. The speed of light in vacuum has the same value c in all directions and in all inertial reference frame. So next we talk about the simultaneity and time dilation. So an event is something that happens, and every event can be assigned 3 space coordinate and 1 time coordinate. So this is a 4-dimensional space, and actually you'll find that the space and time are coupled each other. So it's not really suitable to say that we are living in a 3-dimensional space. We should say that we are living in a 4-dimensional space. Among many possible events, the turning on off tiny light bulb. So it's not really important. So if two observers are in relative motion, they will not in general agree to whatever two events are simultaneous. If one observer finds them to be simultaneous, the other general will not. So let's see this graph. So actually, there are an event blue and event black with event red on these 2 points. And Sally and Sam are in the middle point of this of the B and R. So that Sam doesn't really move. So when the times flow, and Sam will find that these two events actually occur simultaneously. You can imagine the information of the event is transmitted through a light, which means that if the event blue happens, if it emits a light from here, then when Sam receives this light, then Sam knows event blue happened. And this event happened when and then it try to emit the light to here, then Sam observe this light, and then Sam will know event red happened. And if they really happen simultaneously, Sam will find that okay, these two waves approach Sam at the same time, so that Sam will think that two events reach Sam simultaneously. But if Sally moves with a speed v in to the right direction, then Sally will receive the red light first, and later Sally goes to here, and then she'll receive the blue light. So Sally will feel that event red actually happened first. So this is the simultaneity, which means that if someone is really moving fast enough, he will find that okay, even these two events happen at the same time, then but she will feel that this one happened first and this one happened later. So simultaneity is not an absolute concept, but rather a relative one, depend on the motion of the observer. However, if the relative speed of the observer is very much less than the speed of light, which is what we usually be, the speed of light is 3 times 10 to 8, which is really, really fast. A human being can never reach even 1/10 of the speed of light. Even on the speed of sound, maybe 10 times of speed of sound, the human being can have damage to the body. When you try to, so you know the ultrasonic. So ultrasonic means faster than the sound. So it is something like 314 meters per second. So it is much slower than the speed of light. But even get to that speed, human being is not is something like the limit for the plane or something like that. And so usually in the usually the observer is very much less than the speed of light. then the measured departure from the simultaneity are so small that they are not noticeable. That's why for the classical mechanics, we don't really need to consider the relativity effect. However, if we really touch the modern physics or the quantum effect, then we need to consider the relativity effect, something like that. Otherwise, the theory cannot really explain the real phenomenon. Such in the case of experiment, they are why the relativity of is similar. But actually, as you know, the GPS really need the relativity to correct the error. Without considering the relativity effect, the GPS error can be very large comparing to what we have now. So we talk about the time dilation, 时间膨胀. The time interval between two events depends on how far apart they occurred in both space and time. This is that spatial and temporal separation are entangled. So for example, this stuff is not moving. So it tries to emit the light from B to the mirror, and then the light will reflect back to B. Then, so Sally doesn't really move, and we call the time for Sally is the proper time. And for Sam, if he is moving at the speed of v, if v is close to the speed of light, of course less than the speed of light, but close to maybe more than 1/10 or something like that, then he tries to emit the light to the mirror and reflect. So for Sam, he will feel that his time goes slower, actually slower. So you can, well, maybe I try to divide it here. Okay, so, So for the left-hand side case, D is something like C delta T0 over 2. So because the time T0 is the total time for the light emit from B, go to the mirror and go back. So the time for the light going from the B to the mirror is half of delta T0. And the speed of light is C, so that the distance is D equals this, right? So this is simple. And for L, we can write C delta T over 2. So the only difference is we change delta T0 to delta T. And delta T0, we call it the proper time, which means that suppose we measure it, which means that the two reference frame, the two event doesn't really have relative movement, then they share the proper time. But for the other case, observer in frame moving relative to the frame, such as observer on the track watch steady on her equipment move past. So, according to Pythagorean theorem, we know that L square equals D square plus V delta T over 2 square. So we have C delta T over 2 square equals 1/2 V delta T square plus C delta T 0 over 2 square. So actually 1/2 can be cancelled. 1/2 can be cancelled. 1/2 can be cancelled. And then this is delta T. This is also delta T. So we move this term to the left-hand side. And then we rearrange all the stuff. We will get delta T equals to delta T 0. Something like this. Something like this. So delta T is the proper time. And V is of course slower than the speed of light. So V over C is smaller than 1. Smaller than 1. So we take the square, 1 minus this term, and take the square root. This term will be smaller than 0. So it is in the denominator, so that 1 over square root of this term will be larger than 1. Will be larger than 1, which means that delta T is really larger than T0. So that we call it time dilation. We call it time dilation. 时间膨胀了，时间膨胀了。Yes, yes, yes. So, if the time is delayed, then it will feel that the time goes slower. So we can derive the time dilation equation like this, and we can call V over C to be beta, and beta would be between minus 1 or 1. V may be negative, but it doesn't really matter. But usually we'll choose V to be beta to be between 0 and 1, and gamma is the whole term. We call it the Lorentz factor. So this is the factor that the time delayed. So usually, if V is very small, if V is much smaller than C, then this term is 0. Then 1 minus 0 is 1, and take the square root is 1. So delta T will be delta T 0. So if we move really slow, we will not feel the time dilation. However, if maybe a particle can move very fast, then we really need to consider the time dilation effect. Okay, actually I have tried to solve it here. So I have finished it. So I can just go to the sample problem. So this is called the twin paradox, and this is what we say. Your starship passed Earth with a relative speed 0.999 z, so really close to the speed of light. Don't ask how to implement it because so far no one can satisfy this condition. Otherwise, we can go to very far away, at least leave the solar system. After traveling 10 years, your time, then you stop at lookout post, maybe just a name of a star, so LP13. Turn and then travel back to Earth with the same relative speed, so still 0.999 c. The trip back takes another 10 years, of course, because the same speed go for the same distance. How long does the round trip take according to the measurement made on Earth? You get any effect that due to the acceleration involved with stopping, turning, and getting back. So we use the time dilation equation. We can write delta t equals delta t0 over 1 minus v over c squared, something like this. So delta t0 is 10. And v over c is actually 0.9990 squared. So you press the calculator, you can find it is actually 447.3 years. And actually for the round trip, so it is actually 2 delta t, which is, this one should be 223.7. This should be 447.3 years. So this is the famous tree paradox, which means that suppose that there are two twins, and one of them take the starship, which go in a very high speed, go away for 10 years, and then come back. Okay. This number is not really good, so this is 446.3 years later. So actually, this one can go to the future because he actually go to 447.3 years later. If you try to trick the number, maybe not 0.999, maybe make it slightly less, then the twin paradox is something like, okay, the two twins are very young, and then they go for the time travel. Then after he come back, he's still very young, but the other twin become an old man already. So this is called a twin paradox. Why does people call it twin paradox? Because you may think, the one go on the starship actually have the same relative motion, and for the one on the starship, he also feel that the other one on the Earth have the same relative motion. Why does the man on the starship become younger? But actually, experimental results show that the particle will become younger if the particle really go in a very high speed for a while, and we can really measure it. But actually, to really explain this twin paradox, it will be too difficult for me. Okay, maybe we just stop here, and that's all for today.